In this webcast, I'm going to be talking about creating customized spatial models with point clouds. I'm Joe Mustavi, and I'm going to walk you through a few PowerPoint slides first, and then we're going to get into a bit of a demo on how to use these areas. So let's start with the general problem and solution. We'll talk through why we'd be wanting to use the operators in ERDAS IMAGINE, the new point cloud tools in ERDAS IMAGINE, and then we'll kind of give like a little bit of an overview of how that spatial modeler works in ERDAS IMAGINE. We're going to use a case study from the Texas Department of Transportation to kind of show you what their workflow was and how it was improved using these spatial model operators, the point cloud operators in specific. And then I'm going to give you an overview of those new workflows that are available in IMAGINE. And these are the four workflows that I focus in on here. The RGB encode, workflow number 1. The classify the point cloud, workflow number 2. Selecting and subsetting the point cloud, workflow number 3. And then rasterizing to perform topographic analysis on that point cloud as workflow number 4. And I'll finish up with just a couple of screenshots of examples of the outputs from that, and then just follow up with a conclusion, and then we'll do a quick demo to kind of get you off and running. So the problem that we're trying to solve here is that one of the most difficult problems to overcome is working with point clouds is producing a bare earth model void of features that could interfere with its intended uses, such as accurate orthorectification. So we're able to solve this by expanding the power of the existing spatial modeler and the new point cloud operators that I briefly mentioned already, and the ability to preview those results. So in order to solve this problem, we need to take the functionality within our products to create customized workflow without writing software. We want to easily deliver this workflow, and many need to work with point clouds in their customized workflows, and it's not currently an option. So we're hoping to expand the use of point clouds by having this functionality available directly within IMAGINE, making it easy to use and work with. So the solution to this problem is, regardless of how the point cloud was collected, even the best sensors and photogrammetry techniques creating these point clouds collect unwanted features. Is how we deal with these extraneous features that make these new tools available in the spatial modeler for point clouds so powerful. Namely, the ability to run classification on points as part of a workflow, or failing that, the use of filters to clean up unwanted features based on specific modeling parameters. So the benefits of this are being able to pull together the functionality you need to create your own workflow, basically customizing that workflow. You would build it once and repeat it indefinitely. So we're automating these manual steps into a single process, and visually authoring or the orchestration of this workflow is done on the template in the spatial modeling environment. So no programming is required. It's all GUI driven and point and click. It's very easy to set up this workflow, and the code is driving it in the background. You can get real-time analysis with preview options, and multi-data models can be easily created including point clouds. So we're not only utilizing workflows that deal with point clouds, but you can also run these workflows through a vector environment, a raster environment, and we're actually going to take the point clouds and make them into rasters so that we can use the remote sensing tools available in ERDAS IMAGINE. So what we want to do is combine these repeatable processes into a workflow and then publish that. Would be the final stage as a possibility. You're creating a spatial model and publishing that to a web processing services would be an ultimate goal for any organization. So eventually we want to create, build powerful data analysis once and then repeat indefinitely. That's the bottom line here. That's what we're trying to do here. Create it once and run it on, say, 1,000 images. So here we have kind of an overview, a really basic overview of the spatial modeler and using the spatial model operators to process these point clouds. You can also filter point clouds in their native format and do a bunch of different operations. You can see on the right there the point cloud operator options on the point cloud drop-down menu to reclass or recode or select by. A bunch of these different operators will be useful, we'll be using and showing in this demonstration. Being able to rasterize these point clouds for additional remote sensing capabilities is a very powerful tool. We have 30-35 years of remote sensing functionality that goes into ERDAS Imagine. So being able to utilize that point cloud as a raster file gives you access to all those remote sensing tools. And again, creating once and batch processing many files is why we're creating this workflow in the first place. I want to create it once, make sure it works for one file, and if I like the results, let's batch process that and run a whole bunch of point clouds through it so that I can set it and forget it, come back in the morning and have a nice cleaned up surface model. So the next thing I wanted to touch on here was creating spatial models with point clouds, but using a case study from the Texas Department of Transportation. And the reason the Texas Department of Transportation is useful here is because they deal with, obviously, the road infrastructure. They want to and need to ensure the quality and upkeep of the roads is obviously their pivotal point of why they're needing and requiring imagery or point cloud data, and they make decisions based on these surveys and these ortho photos that they're using. LIDAR collection is a possibility. Of course, it's a much more expensive possibility for creating the DEMs in order to create these accurate ortho photos. But if they already have the ortho photos and they can create surface models in, say, a LIDAR format, it's obviously right at their fingertips, and they want to use that. So they do require accurate orthorectification of their imagery. Of course, when you're working with road data, you want to make sure that those roads are actually located where they're supposed to be, so any corrections or mitigations that need to be done to those roads are very accurate. They're continually updating the orthorectified imagery. They want to make sure that they have fresh imagery all the time, so they're always getting fresh imagery. Limiting unwanted features in their elevation source. Of course, if you have unwanted features in the elevation source, you would want to remove those that doesn't interfere with the actual orthorectification procedure. You can imagine imagery that is warped over an inaccurate DEM, or a DEM that has extraneous features like trucks or cars or trees or buildings, that can essentially change the way that the imagery is draped over the DEM and the terrain relief displacement correction that orthorectification does. So the removal of these trees and such features close to the roads prevents this kind of ghosting or misregistration. So as long as you have an accurate surface model, the draping of those images over that terrain relief is going to be much more accurate without buildings and features in the way. So, inaccurate orthorectified imagery. With an inaccurate DTM, if we're considering the fact that if we have inaccurate DTMs as opposed to making accurate DTMs, they can be misregistered, creating improper overlap. So this is obviously going to create downstream propagated errors. It's going to create downstream problems. Namely, just even mosaicing the imagery. If you try to mosaic two images together where the roads are misaligned because of other extraneous features that are pushing and pulling those pixels out of place, creating this ghosting effect, then you're going to have poor mosaics. Your downstream processes are going to be affected as well. Rectification typically includes terrain relief displacement correction from this elevation source. Now, I say typically because some areas are so flat that it doesn't really matter, and there's no trees or buildings around to influence what happens to the imagery, but obviously in most cases you're going to be working with imagery that does have buildings, that does have some kind of trees or cars in it, and therefore you want to take into account the elevation of these features and remove them in order to have a surface model. These inaccuracies result in road shift, smearing, and ghosting. I briefly spoke of this, and proper orthorectification from an accurate surface model will alleviate this. So again, the removal of features such as trees and buildings and cars, trucks, creates a surface that is homogeneous, and therefore the orthorectification will be draped over the elevation source, not the imagery that's being affected by it, based on the elevation differences of the surface model in question. Okay, So the current Barrow solution that the Texas Department of Transportation has, they use a bunch of different software products currently. They use our Image Station Automatic Triangulation, ISAT for triangulation, obviously. Ortho Pro, Image Station Ortho Pro, do orthorectify and mosaic their imagery. They also use Image Station Automatic Elevations. It says here without the SGM because Image Station Automatic Elevations Extended actually does include semi-global matching algorithm, but in their case they currently are not using the semi-global matching algorithm to create their DTMs. They also use Image Station DTM Collection, ISDC, for generating this DTM. And the way this workflow works is they first create a grid surface using ISAE. They then use this grid as a preliminary step in Image Station Ortho Pro, which they then use these orthos as a reference to find any distortions. So they take this grid and they run orthorectification on it and they look for distortions. And they sometimes use contours additionally to help aid in this step, essentially using the orthos as a way to find errors in the grid that they've created in this preliminary step. So then significant editing is required to create a useful surface. So they find the errors, they do the editing on the DTMs, and then this is then used as a seed surface to create a secondary DTM. So this new DTM generated along with revised ortho photos for a final inspection where these ortho photos are checked over to ensure that no artifacts exists from the DTM that was previously made. So essentially creating a DTM, running orthos, finding the errors in that DTM, fixing them, then rerunning the orthos with that newly edited DTM as a seed source, and then running orthos again as a final product. What we want to do is try to alleviate the step of doubling up the DTM and ortho generation for that matter and just doing it all in one step. If you have a solid surface to work with to begin with, you only need one elevation extraction and one ortho rectification from that. Alright, so the solution is to obviously streamline that. And you can just streamline that as to streamline the point cloud editing. So if we can fix the problem with the DTM collection, the surface collection, in the first place, then subsequent DTM extractions and multiple orthorectifications are not needed. In fact, you can go right to orthomosaic if you wanted to. So we can use these streamline operators to fine-tune the point cloud so that little or no manual editing is necessary. By adding the semi-global matching algorithm to this workflow, it increases the accuracy of the point cloud file to begin with. So first of all, they're starting with a much more accurate point cloud file using the semi-global matching algorithm, and then taking that and essentially using the spatial modeler in order to fine-tune, the editing using a classified point cloud and that kind of thing. We'll step through that here in just a minute. So the coupling of this SGM output with the new spatial modeling capabilities creates a streamlined workflow for the point cloud data. So this is a way, the solution here is essentially this coupling environment using this higher accuracy DTM with the spatial modeling capabilities for fine-tuning the editing automatically is now creating much more accurate DTMs, and with this increased accuracy also comes quicker orthophoto generation, which if you have quicker orthophoto generation, it's a better product. And not only that, more importantly is this return on investment that you get from that. So the workflow for creating these bare earth DTMs. The workflows described below employ the techniques necessary to automate the removal of features, turning DSMs into DTM. So digital surface models, everything that you see included in the surface, into digital terrain models, so just the terrain. So we're basically trying to remove trees, buildings, cars, that kind of thing that are considered extraneous features and can influence the orthorectification procedure. Now, I'll be showing here 4 different workflows, but each workflow can be used separately or combined into one seamless, black box approach if wanted. And this black box approach can then also be batched, or any of them can be batched for that matter, and distributed across multiple nodes for a streamlined push-button approach. So being able to process multiple files across multiple processors across multiple machines. So you can see where I'm going with the power to distribute the processing will make things much quicker and more efficient. These workflows can be used regardless if they're collected from a LIDAR sensor or photometrically derived using an algorithm like semi-global matching. So even if you did have a repository of LIDAR data, I shouldn't say old, but a repository of LIDAR data, we can do things like RGB encoding that. We can classify that. It's still in its native LAS format as it goes in and goes out, unless you want to rasterize it, voxelate it. It's up to you. But you have that option, and it doesn't matter if it comes photogrammetrically or if it comes from a LIDAR sensor itself. So the workflows covered here, there's obviously more workflows that can be addressed and thought of and worked on for your specific application, but in this case we're just going to be showing how to RGB encode the point cloud, how to classify the point cloud, how to select and kind of filter out the point cloud and subset it, and then also to rasterize that point cloud so that we can perform topographic analysis on that using those remote sensing tools I spoke of, and essentially all the other operators available to you in the spatial modeling environment that aren't just LIDAR or point cloud operators. You have the option to use all of them at that point. So here's the complete workflow, an overview of what the end product could be and would be. Essentially, starting from the top left there, you have your point cloud output, and assuming that you don't have the RGB encoded input, in this case we're creating a semi-global matched output, which also does RGB encoded on the fly. But if you didn't have that, it's very simple RGB encoding operation to use the color from, say, a mosaic image to RGB encode the point cloud. It is then run through the classifier to separate, all the different points into classes, be it a water class, a vegetation class, what have you. It's going to separate those out by vegetation, and an object and that kind of thing. Then we have some selection tools and subset tools that allow you to keep what you want or not keep what you want for that matter. And then, of course, we can rasterize that output, which enables you to perform your topographic analysis. Like you see here, we've got kind of an example of a degree slope being performed or a relief output being performed in this model. So you have the option to do any of those features and those operators, and it's certainly not limited to just those two, all those operators that are available in the spatial modeling environment. So if we look at the RGB encoding, workflow number one, it creates a photorealistic view of the point cloud. So your points, if dense enough, actually look like an image if you RGB encode them. And when you zoom in, you'll obviously see the spacing between the points, and it starts to not look like an image anymore, but it's kind of like 3D photogrammetry. LIDAR and LAS files, encoding can be added to any LIDAR file. So if you have previously collected LIDAR data that isn't RGB encoded already, it's very simple to grab the color from, like I said, an existing mosaic file and encode the LIDAR files so that they look like this 3D view of a point cloud. Classification, so allows for the classification based on a DN range of values. So you're separating the point cloud out into different values, different classes based on object heights and vegetation heights and that kind of thing. And there's some selection options you can choose to include or exclude in the classification engine that gets you a better classification output. And semi-global matching support. So point cloud operators support SGM outputs. So that output, RGB encoded output from semi-global matching algorithms, like available in Imagine Photogrammetry and Image Station Automatic Elevations Extended, are supported in here, of course, and are kept intact as you go through where necessary. So if it's a RGB encoded input, it will remain the same unless you do something to remove the RGB encoding at your preference. Workflow number two is classifying the point cloud. So this is going to separate the points into different feature classes. Feature identification enables the extraction of features like buildings and vegetation. The bare earth extraction, so you can predefine criteria allowing for above ground identification and removal if necessary. So this is kind of the key reason why a classification engine would be used. You may just want to only keep the bare earth ground extraction and remove everything else. And we can classify any kind of point cloud, so it doesn't have to be RGB encoded in order to perform classification. So like I said, you can start with a LAS file from a LIDAR sensor that doesn't have RGB encoding. It doesn't matter. It's still, as long as it's a LAS file format, it will come in and be useful, much like any RGB encoded LAS file created from any semi-global matching algorithm. Workflow number 3 is selecting and subsetting the point cloud. So you can subset features allowing for filtering and clipping of points. You can select by an extent if you want to clip to an extent using an AOI or a min-max Z, or inversing the whole point cloud selection, flipping it from what you don't want to include. You can also select by classification. So if all you're interested in is, say, the water layer, the water values, you can select just that one class and output that point class, and then maybe go rasterize it if you want to, and then maybe run a buffer on it, that kind of thing. You can select by return also. If you have a LIDAR sensor format LAS file that has a bunch of different returns, you can select based on single, first, last, intermediate return for a more accurate output option. And then finally, the use of workflow number 4, where we can rasterize the point cloud in order for there to be the topographic analysis done at things like slope, aspect, installation, percent slope, and relief are some examples of why you'd want to rasterize that point cloud, or even if you need to do some kind of volumetrics. Volume on raster is a lot more accepted practice than on points, but you have options to do both. It's remote sensing capable, so the grid file can then be used in any remote sensing process, and again, being able to do that topographic analysis. So here's an example of the file to start with. So it's an RGB encoded point cloud. So as you can see, this is a point cloud. It comes from the imagery, but it's photogrammetrically derived. The semi-global matching algorithm produces it, and then the output from that produces a classified output. In this case, we're viewing it as an elevation source, not as an actual classification, but the elevation source shows you the areas of obviously high elevation and low elevation. I can see, which I couldn't see in the previous image, let me back it up here, that there's a river running through it. If you look at the areas in the trees, you can't tell there's a river, but because it's classified and that semi-global matching algorithm was able to pull out the features underneath the trees, and you can see that there's a river winding its way through that area. If we look at the outputs, and what I've done here is just put them in 4 different viewers so you can see the different classification outputs. So the RGB encoded point cloud is in the top left there, so that's what we started with. We ran it through the classification, which you see in the bottom right, and we've already seen the elevation in the top right there, but the classification output is in the bottom right there, so you can see the road coming through is the yellow, and the river coming through is the blue. It classified that, and the vegetation, it's pretty high vegetation, so it's between greens and mixed greens and low vegetation. The greens are of similar colors, so it's kind of hard to differentiate between low and high vegetation, but you can very easily change those colors, of course. And then if we look on the bottom left image, I've actually draped the classified image over top of the RGB encoded true color perspective image, and only showing the bare earth ground class in this case and the water class. Just an example of how you might want to separate or filter out just a couple classes, and you don't even have to make a new file. It's just a matter of turning those classifications on or off. In this case, I wouldn't even need to use a model for that, but if I wanted to separate them out, there's different ways of doing that, spatial modeling being one of them. In conclusion here, I just wanted to say that the coupling of the point cloud operators now available in the spatial modeling environment in ERDAS IMAGINE with the remote sensing capabilities that already exist greatly improves the bare earth extraction and output from these point clouds. So beyond the scope of these workflows, these operators could be combined with remote sensing and other operators that exist in the spatial modeler. So the stringing together of these operators and batch processing of these models on multiple files, while also taking advantage of multiple processors, can dramatically increase productivity. So with these new operators in place, the Texas Department of Transportation is able to reduce processing time while improving their orthorectification results. By eliminating objects and vegetation from the point clouds, they are able to produce accurate orthorectified imagery, especially along the interstate roads where they are most concerned about orthorectification quality. So again, bottom line here is create and build a powerful data analysis once, and then repeat indefinitely. Loop it through a spatial modeling environment across multiple machines to increase your return on investment. With that, I'm going to switch to a demonstration. So here's the actual classification output, but what I want to do is show the creation of a spatial modeling environment. So if we take, for example, point cloud option, and we choose, say, a point cloud input. So under my input options, I'd go to point cloud and drag and drop an input source in here. And depending on what I want to do to that input, I might want to, let's do a point cloud to raster, just to keep it quick and simple for this demonstration. And then I would need to output the actual raster itself. So here's my output options, and from that I would choose raster, so because I'm going to rasterize the input. So connecting the dots, I basically take this one and connect it from here to here, and then raster out from here to there. Double clicking on the file name here, actually I can go through and select an option, double click on this. Here's where we have the different options to choose from going from point cloud to raster. So I can RGB encode it at this point if it's already RGB encoded. If not, I would have to do a separate RGB encode operation. This doesn't mean that you're actually RGB encoding it, it's just taking it if it exists and outputting it through the source. So I will select that, and I have the option to choose, which return, if I have a true LIDAR source as opposed to a photogrammetrically derived point cloud. If I had a LIDAR sensor last file, then I can choose which return I want, first, last, anyone in between. I can also classify the output. If I have a point cloud that is a thematic point cloud, I can classify it based on that as well. So I'm not going to do that here. I'm going to automate the pixel size, because it's going to figure out how to create that pixel size based on spacing and extents. And then I just say OK to that, and then I specify a file name for my output. So I just call it, say, test. It's fine, and then I just click the run. What I also like to do is use this auto layout tool to make sure that all my layout stays the same, unless I can't see what I'm doing. Then I like to move it over a little bit. But the auto layout is a nice little tool to run with as well. And if I wanted to, I could preview the output of this. So if I'm not sure where the preview option is, I know it's under view here, but if I wasn't sure, I could type in pre, and it already picks up on the fact that preview is here, and it shows you that it's in the output area under view. And then if I wanted to, I could add a preview dialog here, where I would, instead of actually creating this raster output, maybe all I want to do is preview that output. So instead of hitting run, if I hit run right now, it'll run through this process and actually generate this test.img image. If I hit preview, it's only going to create this preview image, and it's going to load it up in here. So let's go ahead and do that. Okay, so here we go. That didn't take too long. It all depends on where you're writing your image to. In this case, I'm actually grabbing the data from an external drive, so it should take a little longer. This process is pretty quick. The classification can take a little bit longer That's why it's nice to be able to batch it and set it and forget it and come back to it a little later. So now if I wanted to actually create the output, I could just delete this or turn this off and just run this in batch mode if I wanted to, or run it in the background and set it for another time. I can set it to do that. In the meantime, what I'm going to do is let's clear this out. It's fine. Let's clear this as well, and let's do an example of how to do, say, the classification model. Same kind of deal. Select the input. In this case, it might be a point cloud input, of course, as opposed to a raster file, because we have these new point cloud tools. Come on, there you go. And grab the classifier. You can also come up here and use favorites if you have enough favorites in your list. I've only got a couple so far, and then I just drag and drop the connections. And this time our output's not going to be a raster; it's actually going to be a point cloud output, because, like I said, you want to keep it in its format or rasterize it depending on what you're doing with it. So again, we specify what our input is. So if we go and let's grab our original data set or any one of these, and then I would run it through and choose my classifier selections. So here we have the auto classifier. Again, you can make changes to min-max areas. We also have the ability to select greenness value. So if you have near-infrared imagery, it will work with that. It will actually RGB encode in a near-infrared color space, but it also use RGB layers and use the greenness from the red and the blue bands, red and green actually, I believe, to define the greenness index. It's a red plus green divided by red minus green, and or vice versa, but allows you to also use that option. So I'm not going to run this one, but I think you get the idea here that this one does take a little longer, but I might want to batch this. And now that I have this set up for one input image, I can use the batch tool to process it for a bunch. So if we actually want to go in and make changes not using the spatial modeler, we can always say load an image. Let's say, sure, let's load this class one. This is the one that comes, the classified one. I just ran before this, and you can see this is the elevation output. If I want to show the RGB encoded output, this is what it looks like. And you can see the road comes up. It looks like a true color image, but as you zoom in, you start to get a little bit of pixelation, and if you keep going in even more, you're going to get even more pixelation. You'll notice around the trees, obviously underneath the trees, we're not going to have certain values underneath shadowed areas. If there's no value in there, if you don't have a bit depth enough to get the values inside the shadows, you're going to have no data values. You won't get that obviously with a true LIDAR optical sensor, where it penetrates tree canopies if designed as such. So I'll just back this out. I have my quick access tool set up such that I can zoom in and out pretty readily, and say I want to view this as classification. You can see the bare earth being brown. Here, if I drop down the class, you can kind of see which is which. Maybe I might want to define a certain area based on heights. I can easily do a cross-sectional view. So if I did this, now I have the ability to zoom in on certain areas, rotate this a little, and it updates the perspective views on the left and right. I can squish this in. So all this is doing is just selecting within the frames these areas of interest. So if I come in here, I can back up a little bit. It shows you the yellow is obviously the road. It's been classified as road. And if I wanted to, I could select this water, and I could do that just by using a box selection. I like to use a polygon selection and just kind of zoom in. I'm using my middle mouse tool to zoom in on just this area. Double click, and that is selected. You should see the water come up as white in that box area. So only the water is coming up. So at this point, I could then go in and manually recode these to something like water in this case, and it will actually change those values to water in the classification engine. And if I apply that, we will then see that change happen in the classification option. So it's already, as classification, it's already water, so I don't need to do that, but I think you see where I'm going with that. And of course we could also view this in 3D. So if I wanted to view this this image in 3D, I can then zoom in on this area, and it defines what's going on in this image. So you can see the water, the trees all around. I got some buildings right here. I'm getting just the roofs, but that's exactly what I expect. So hopefully this gives you a good idea as to how to use the tools in Imagine and the spatial modeling environment, and that you got something out of this webcast. Thanks for your time.